All right, for this last video in section 15.3, we're going to begin with some notation. So if we integrate over a closed curve C, then we're going to write the line integral of a vector field f over this path using this notation where we include this little circle over the integral symbol. And that's just to emphasize the fact that the path is closed. Okay, so now looking at question 7, it says let f be a continuous vector field on an open connected domain D. Part A says, suppose that this line integral is independent of path. Show that this implies that the integral over any simple closed curve C in your domain is equal to 0. Okay, so if the line integral is independent of path, then from theorem 17.5, and note here our domain is assumed to be open and connected, which was a requirement for that theorem. The independence of path here for the integral implies that our vector field is conservative. And so if our vector field is conservative, then that implies that to compute the integral over a simple closed curve like you see here, okay, I just need to evaluate the potential function phi at the endpoints. But see, if it's closed, then the initial and terminal points coincide, right? B is equal to A. So evaluating the potential at the terminal and initial points, you're just going to get the same value there, right? You're just evaluating phi at this point A. And so that difference will equal 0 for any simple closed curve. All right, so that does it for part A. For B, we're looking at the converse here. So if it's true that the integral over all simple closed curves C is equal to 0, then show that this line integral is independent of path. Okay, so what we need to do there is choose any 2 points in our region D. So our points here labeled A and B. And then we need to show that if we compute the line integral over a path, say C1 from A to B, and then we compute the line integral over another path, say C2 from A to B, these two line integrals must be the same if the line integral is independent of path. All right, so how do we incorporate this assumption into this picture? Well, we can construct a simple closed curve from this by first following C1, and then we're going to follow C2, but in the reverse orientation. So in other words, we're going to start at B and then end at A. So here's what we're going to do. We're going to say, let C be the simple closed curve that starts here at A. We follow C1, and then this union symbol is saying, okay, now follow that with C2, except this negative here is indicating that you're going to reverse orientation. Okay, and that's what these yellow arrows here are denoting. Okay, so when we're following this red path, we're starting at B and ending at A. All right, and now since that's a simple closed curve, this assumption we're starting with implies in particular that the integral over this path, where we start at A, we go out to B, and then we come back to A, that integral would be 0. But see, we can now break that up as the integral first over C1 and then integrate over C2, but because of this reversal in orientation, as we've discussed with parameterization and vector field line integrals, right, that introduces a negative in front of this integral over C2. And so since now this difference is equal to 0, that implies that these two integrals over C1 and C2 are in fact the same. And so that implies that this integral is independent of path. Cool. All right, so that does it for part B. And then at the bottom here is just a summary of the main results that we've studied in this section. So it says the following are equivalent for a continuous vector field F on an open connected domain D. Okay, so F is conservative on D. In other words, we can find a potential function phi such that F is equal to the gradient of phi. Okay, that is equivalent to this integral being independent of path. Okay, that was the content of theorem 17.5. And now, based on our discussion from question 7, we know that this independence of path condition is equivalent to the integral over all simple closed curves in our region to come out to be 0. All right, well, that is going to do it for this section. In the next section, 15.4, we're going to look at the second fundamental theorem of vector calculus known as Green's theorem. Okay, so I will see you there. Thanks.